Hey y'all, welcome to lesson 10.3, which is all about the combined gas law. If you remember back to lesson 10.2, we talked about basically the three important laws of gases: Boyle's law, Gay-Lussac's law, and Charles's law. And in this lesson, we're basically just going to combine them all into one. So that's why we call it the combined gas law, because it combines all of these together. Um, so as a little intro up here, it says if a scientist, or you, which you are scientists, considers these three laws together, um, we can write an equation called the combined gas law. And this combined gas law represents the relationship among temperature, pressure, and volume, all three of them. So we can relate all three of those of a gas: the temperature, pressure, and volume. Um, So basically, the combined gas law looks a little bit like this, um, where P, as before, is the pressure, V is the volume, T then is obviously the temperature, and K is a constant. Basically, it's kind of like a fudge factor. These three things are related. There's a little bit of a fudge factor, and it's exactly the same for all gases. And scientists, over many, 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 many years and trials and experiments, have come up with what this is. And so it's used in all these equations. It kind of you can relate it back to math equations, um, like the equations for the circumference or the area of a circle, all have to do with pi. Right, pi is kind of like the fudge factor. It's how we can relate the radius of a circle to the circumference, or the radius of a circle to the area, based on, they're all related based on this fudge factor of 3.14, blah, blah, blah. Um, but it works for every circle no matter what, always. So that's why this is called a constant, because it's constant and it relates the volume, pressure, and temperature of a gas together, um, no matter what. Right. Um, the only difference is that the K in these equations is not going to be the same because different elements are different. So it's the same for all oxygen, and then it's the same for all nitrogen, right? Um, but it's not the same for every gas. So the way we work around that here for this combined gas law, and this will come up again when we talk about the ideal gas law in the next lesson, but in order to use this to predict temperature, volume, or pressure change, the number of particles in a gas can't change. So, like I said, the number of particles can't change. But in all of the problems that you will do with the combined gas law, that's just a given. They're not going to change. So this will be fine. You won't have a problem with that at all working through problems about the combined gas law. So when we take this equation and use it to compare two different gases, or let me rewind. We use it to compare one gas, because remember the number of particles can't change, at two different conditions. We can use this iteration or this version of the equation. Basically, it says pressure 1 times volume 1 divided by temperature 1. Those probably look somewhat familiar based on last unit, right? Is equal to pressure 2, volume 2 divided by temperature 2. So we can make this comparison. Just a combining of those three laws you learned yesterday. or in the last lesson. Don't know if it was yesterday or not. Anyway, so let's do a problem. Okay. So basically it says a sample of neon gas occupies a volume of 875 milliliters, 31 degrees Celsius, 805 millimeters of mercury. Okay. What will the pressure be if the volume changes, so it increases from 875 to 925, and the temperature increases to 50 degrees Celsius? What will my new pressure be? Okay. So we basically have 5 numbers here, 1, 2, 3, 4, 5. And we need to figure out the final one. But we can just plug those numbers into our formula. This is how I always like to do this, just like I did the other ones. P1, V1, T1, P2, V2, T2. Initial, final. So we just look back to our problem. Our initial pressure, 805, 805 millimeters of mercury. V1, initial volume, 875 milliliters, 875 milliliters. Initial temperature, 31 degrees Celsius. Okay, so that's all the initial things. Then final pressure. Oop, that's what I don't know. That's what I'm trying to figure out. See, it says, what will the pressure be? Don't know yet. Volume. Volume is expanded to 925. So volume expands to 925 milliliters. And the temperature is increased to 50. So temperature 2 is 50. Changes. Okay? So that's my first step. Let's write down everything I know. Give it a label. Second step. Temperatures always need to change to Kelvin. So I'm going to add 273 to this. And I get, 304 Kelvin. I'm going to add 273 to this one. And I get 323 Kelvin, right? 375 is 12. Yeah, 323. Okay, so convert your temperature to Kelvin. Has to happen. And then I can just plug what I know into my equation here. So pressure 1, 805, times volume 1, 875, divided by temperature 1, 304, equals pressure 2, make that X, we don't know, volume 2, 925, temperature 2, 323. Okay? Right? Then we multiply all these things together. And I'll just do the math, right? 2316 equals, divide here, 2.86x. So I just multiplied 805, 875 divided by 304. Got that. 925 divided by 323. Got that. Times x. Right? Simple math. Divide by 2.86. And my x equals 809. Sorry, I'm off the screen. 809. Units, millimeters of mercury. So that is what my pressure changes to. So when the volume goes up and the temperature goes up, the pressure changes just a little bit, not much. But that is it. So that's the combined gas law right here. It's when you have pressure, volume, and temperature all together in one problem. And you just do some multiplication and division, and there you have it.